Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this lecture, we're continuing our investigation of stereochemistry by looking at the stereochemistry of cyclic compounds. The molecule you see before you is a geometric isomer of cyclopropane. It has 3 carbons in a ring structure. And we learned that in order to name this molecule, when the substituents are on opposite sides of the chain, this is either trans (1,2) dibromocyclopropane, or it can be called E-1,2 dibromocyclopropane. So it's either trans or E. What's interesting is I could tip this molecule on its side. If I drew it on its side, it essentially, that's a bad drawing, it's the same thing. I could put the H's in. Whether I draw it on its side or straight up and down makes no difference. So this is still trans 1,2 dibromocyclopropane, just on its side. Now, I could put a mirror here and draw the mirror image of this 3-membered ring. And then we'd have an H here, a Br here, and a Br here, and an H. Now this should be the same thing. I mean, the groups are still on opposite sides, hindered rotation. It should be trans or E-1,2 dibromocyclopropane. But this mirror image reflection looks very familiar to, or similar to, looks familiar and similar to something we saw in the previous scribblecast lectures. But let's pretend I'm going to just draw an ordinary fissure. And the only difference is the group at the top is a CH2 and the group at the bottom is a CH2. And these two CH2s are the same CH2. In other words, the CH2 that you see right here, that CH2 is attached to both the top carbon and the bottom carbon because it's part of the ring. So I'm drawing the same CH2 at top and bottom. It looks a lot like the same fissure, and if I put a mirror here and I draw its mirror image, I get that guy. Again, the CH2 is the same CH2. This is a 3-membered ring. Now what's interesting about this is these two look a lot like the structures we saw in tartaric acid where the groups were opposite, and so the mirror images turned out to be non-superimposable stereoisomers. They turned out to be enantiomers. What that means is that there are 2 different enantiomers of trans 1,2 dibromocyclopropane. 2 different enantiomers. Oh wow. Okay. That means The name E or trans 1,2-dibromocyclopropane is not specific enough to distinguish between these two enantiomers because they're both E or 1,2. Now we learned the nomenclature to distinguish between these guys is RS nomenclature. How would you name the trans isomer using RS nomenclature? Well, that's pretty easy. If we took this guy, in fact, if we took this guy and we looked at the top chiral center, we could draw this. We got CH2, we have an H, and then a BR, and our squiggle. The BR is highest atomic number, is number 1. The squiggle is this carbon. This carbon has over here bromine off of it. The CH2 is this carbon of the ring. Right, we're pointing to it here. This carbon of the ring, he's attached to another carbon. You can't see it, but he's actually attached to that carbon, to the squiggle. So, in actual fact, this carbon, the squiggle, has a bromine. He has another carbon, which you can't see because he's hooked into the ring. This squiggle becomes number 2 because of the bromine off of it. And the CH2 becomes number 3. Hydrogen's 4. Remember, when determining nomenclature and Fisher's RS, you have to get the 4th group to the bottom. So we put the H on the bottom. BR stays where it is. Squiggle's where the H was. CH2. And the bromine's number 1. Our squiggle, which is this bottom chiral center, is number 2 in priority. CH2 is number 3. We have 4 for hydrogen. You draw a curve from 1 to 2 to 3, knowing number 4. This is R. Therefore, the original, because we did an odd number of interchanges, we did 1 interchange. The original, therefore, is S. So, in this structure, this is S. That is S. Okay, now we can do the bottom chiral center. We have BR to the right, H. At the bottom we have the CH2 of the ring. It's wrapped around. And we have a squiggle. Okay, bromine is number 1. It's highest atomic number. The squiggle has a carbon. CH2 has a carbon. The carbon of the squiggle has a bromine off of it. The carbon that's a CH2 of the ring is attached to another carbon. Bromine's higher priority than carbon. He's 2. So the CH2 is 3. He's higher atomic number than H. Switch H to the bottom like you have to in your Fisher. H to the bottom's number 4. We've got a BR, our squiggle, our CH2. 1, 2. Knowing number 4, we draw a curve from 1 to 2 to 3. This guy is R. Therefore, the original, because we did 1 interchange, is S. And that makes him S. This is S. And so, if I am to name, shall we say, my trans 1,2-dibromocyclopropane, I'm going to name this one, I would call it 1S, 2S, bracket, 1,2-dibromo. Okay, dibromocyclopropane. The exact same thing. So this would be 1S, 2S, and that would be a very more accurate description because it would be naming one specific enantiomer. So when we're talking about trans 1,2-dibromocyclopropane, there are 2 enantiomers. They are non-superimposable mirror images. They're both trans 1,2-dibromo, so trans exists as 2 enantiomers. And if you want to name them individually, you'd have to use RS nomenclature to name them more accurately. Well, what about the cis case? What about when we have cyclopropane and we have the cis? Well, if I draw it on its side, thusly, and try to draw the enantiomers. Again, we can get close to a fissure by putting it on its side. Put a mirror here. We get the ring the other way, and we get the BR. This clearly shows we have two chiral centers in the cis case. This is just like this structure. Again, the CH2s I draw at the top are the same CH2. They're the single CH2 from the ring. So my CH2s, these are the same group. They're the back carbon of the ring. And if I draw its mirror image, I get this. And again, this looks a lot like what we saw for tartaric acid, where both groups are on the same side. It's totally symmetrical. The groups at the top and the bottom of sides are the same. And that means there is this internal mirror image, if you like. Right there, mirror plane, that reflects one group into the other. And if I was to determine the chirality here, I'd have bromine, carbon with bromines 2, 1, 2, he's sticking out, 1, 2, 3. This guy would be S, I believe. Nope, no, 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 no. That's coming out. When I turned the other way, he would be S, I think. Yes. And he would be S. No, this one would be R. 1, 2, 3. R. And then the mirror image of that would be RS. Let's just check that. We can check that very quickly by going up here. Bromine is number 1. The CH2 is number 3. Number 2 is the squiggle. I'm going to move the squiggle, do the switch. The squiggle switch would be number 2. And then my H would be number 4. Draw my curve from 1 to 2 to 3. That's R, but I did one interchange between the H and the squiggle, so that's S. So indeed it works out. Notice that this molecule has a mirror plane within itself where the one chiral center is the exact opposite of the other chiral center. When you get this phenomenon, these two groups become identical. These two mirror images, they're stereoisomers. They're mirror images, but they're superimposable. And so what we've generated here is a mesoform. So when you have a ring that is cis, and you have that ring, you get a mesoform. And so there's only one enantiomer for the cis 1,2-dibromocyclopropane. And because it's a special mesoform, there is no difference between the SR and RS nomenclature in this mesoform. Now, you get an interesting result if you try this type of investigation with cyclohexane, because cyclohexane exists in a chair conformer. And if we take a look at the chair conformer of 1,2-dibromo, or dichloro, or whatever. Let's work with bromo. And let's make it trans. Okay. So I've got, I'm going to work here. Straight up will be a BR. And straight down will be a BR. We'll show the hydrogens. And I'm going to draw this guy's mirror image. If I draw his mirror image, he ends up tilted the other way. Okay, so this guy has a bromine. He has an H. And this guy has a bromine. He has an H. All right, so are these two molecules the same? Well, I could rotate this molecule, but if I swung this molecule around, if I took an axis here and spun this guy around, I would get this. Oh. Let's try drawing it a little better. And you can make a model and actually do this. Just spin the guy, take the whole cyclohexane ring, and spin it around. So if I spun this, so this BR swung to the back in the same position as that one, where's this BR end up? Well, this BR ends up back here. It's not on the front carbon, it's on the back carbon. And so they don't overlap, they don't match. So rotating it doesn't help you with these two structures. What if I do a ring flip? Okay, well, let's leave this. And let's go below him, and let's ring flip this guy. Let's not rotate him. Let's just do a ring flip. Okay. Let's try that. Join those up. Okay. How's that? Okay, so if I ring flip, this bromine at the top becomes equatorial. And the H is down. And this bromine, this H gets axial up. And this bromine becomes equatorial. Now if you examine that and you say, well, if I rotated it, it wouldn't match this one either, because this guy's got both groups axial. So if I labeled, say, this group A, this group B, B does not match C. Okay. A and C are non-superimposable mirror images. That means A and C are enantiomers. B and C, because the bromine's gone equatorial here, okay, B and C are not the same. Because C has axial bromines and B has equatorial bromines. Now if I do a ring flip of C, I ring flip C, so this H becomes axial, and the bromine's equatorial. And then this bromine, this H, becomes axial here, so the bromine's equatorial. In the trans case, both bromines become equatorial. I'll say, well, okay, now they're equatorial in D, we call this D, equatorial, equatorial. Can I rotate this guy? Like I tried the up one, can I make B match D? Well, if I do that rotation, on this guy. This bromine will swing to that position, that's correct. But this bromine right here, this bromine, he will swing off to the back carbon. And so they won't match. He'll be in a different position. So B and D, though, if I look at B and D are mirror images, though. And B and D are not only mirror images, they're non-superposable, so that makes B and D enantiomers. Now, when you're given structures like this, you have to be able to determine, are they conformers, are they isomers, are they enantiomers, what is the relationship? So A and C are enantiomers, and B and D are enantiomers. And you have to be able to manipulate them by, like, imagining these rotations, taking the ring structure and drawing the rotation about this axis. And I suggest you build the cyclohexane mirror image and try rotating and see if you can get them to superimpose. And you'll find that A and C cannot superimpose, no matter whether you rotate it, ring flip it, no matter what you do. Let's try the same thing now for cis 1,2-dibromo. Okay, so I'm going to draw cis 1,2. Okay, and we'll put it here. This guy will be up. We got H here. Okay, and we'll have a bromine here. And so to be cis, one bromine's axial, one bromine's equatorial. I'm going to draw its mirror image. Okay, and so I have to draw this, oops, and this, and this. Okay, and so the bromine closest to the mirror is axial. So this is a perfect reflection. It has an H here. And it has a BR, that's equatorial. So these two are mirror images. I'm going to call this guy A, B, C, D, E, F. We'll call it D and F. D and F are mirror images, the stereoisomers. Notice if I tried to superimpose them, if I rotate this guy to that position, yes, this BR is down, like that. That's H. I can rotate this guy a bit. I'm not going to draw this one. If I do rotate him that way, this BR will end up lined up with this guy pretty good. But this BR and H would be in this position. And so rotating doesn't get a superimposable object. And you really should check that out by making the model with your model kits and looking at it. What if I do a ring flip? What if I ring flip this guy? Okay, let's try. Let's do a ring flip of D. So I tilt my ring the other way. What was the up end becomes down, and what was down becomes up. And I end up with a new chair conformer. Looks like that. Now this left-hand bromine H, the equatorial bromine becomes axial, so I'll draw it axial. And the BR, the other end, the H becomes axial. And the BR becomes equatorial. I want you to look over, let's call this guy E. I want you to compare now E and F. So D and F were non-superimposable mirror images, which means they're enantiomers. Enantiomers. Okay, what about E and F? Well, if I look at them carefully, the H straight's up, the bromine's equatorial. That's the same as that. It's in the same chair. This BR's axial, that BR's axial. When I ring flip D, I got F. E and F are the same. Now, at room temperature, cyclohexane can ring flip easily. Because of this, the enantiomer D changes into F by a ring flip, because E and F are the same thing. That means D and F are constantly interchanging. What about if I ring flip F? Okay, let's ring flip F. So I'm going to draw the ring flip of F. And if I draw this, ring flip at F, this BR is now axial because he was equatorial. The axial BR becomes equatorial, and it becomes H. Here's my H. Let's call this one G. How's G compared to D? If you look carefully, you'll see G and D are the same. So ring flipping is changing D and F into each other. G and D are also the same. Because of ring flipping, D and F become the same molecule. And so the two enantiomers D and F can interchange by ring flipping. And if you were to remember, then because of ring flipping, D and F, if these two were given to you, you'd have to remember that ring flipping can occur and that D and F are the same enantiomers. They would be identical. Right? They would be identical because of ring flipping. So what you could do, if it was asked, you could put identical, and then you could put in brackets ring flip. Notice that this applies for cis 1,2. Okay? In the case of cis 1,2, they're the same because of ring flipping. Trans 1,2 does not become the same. Okay. So, we've come quite a ways in our stereochemistry discussions and lectures. We have looked at more than one chiral center, two chiral systems, both now in straight chain and ring systems. We have determined that when you have more than one chiral center, the total number of stereoisomers you get is 2 to the n, where n equals the number of chiral centers. So when you have two chiral centers, you get 4 stereoisomers. And we've been seeing that in our last few lectures, or scribblecasts. We have defined enantiomer as stereoisomers that are non-superimposable mirror images, and we've recently been introduced to diastereomers. Diastereomers are stereoisomers that are not mirror images and non-superimposable. We learned that diastereomers differ from each other, having different physical properties, okay, melting points, boiling points, and are easily separable. We've learned that enantiomers are identical in every way except for 2 properties. 1, how they rotate plane polarized light, and 2, how they interact with other chiral molecules. We learned that the only way to separate enantiomers was to first convert them to a pair of diastereomers. The separation of a mixture of enantiomers was called resolution. Or sometimes you say, we resolved the enantiomers. How were the enantiomers resolved? Resolution is the separation. The actual separation of a racemic mixture. Remember, racemic mixture is a 50-50 mixture of two enantiomers. Into its pure enantiomers. Now, I want to give you an example, a specific example, because the last example I gave in a previous lecture was hypothetical, of how one could separate specific enantiomers. And we're going to look at a case of a racemic mixture of a chiral amine. So let's consider this molecule. And the molecule is Sec-butylamine, or, if you like, 2-butanamine. Wait a second. I thought amines were not resolvable because they undergo inversion. Amines undergo inversion and change their chirality and change into one enantiomer. Well, that's true when the chirality is at nitrogen. But where is your chiral atom in this case? Well, nitrogen has a lone pair and a carbon, but has two hydrogens, so the nitrogen's not chiral. So this nitrogen could be inverting all it wants, but since it's not chiral, it makes no difference. The only chiral atom in this is this carbon that bears the nitrogen, the hydrogen, the ethyl, and the methyl. This is our chiral carbon. Nitrogen can invert all it wants, but that won't affect the chirality at carbon. So if we do separate the enantiomers that exist because of this chiral carbon, the inversion of nitrogen will not affect that chirality. Now I'm going to symbolize the chirality with the rotation symbols, plus minus. And if I put plus over minus, it means this is a racemic mixture of both enantiomers, the one that rotates light to the right and the one that rotates light to the left. Now what's interesting is we can extract from biological systems pure forms of enantiomer. And it turns out that the molecule tartaric acid that we looked at earlier is one molecule which from biological systems can be isolated enantiomerically pure. Turns out biological life forms are very good at purifying enantiomers. And so we're going to use or reaction with tartaric acid. So I'm going to have HO2, 2C. Okay, let's try that again. So I've got HO2C, CHOH. Now remember with tartaric acid there were 4 stereoisomers, but one was a mesoform, so that reduces it to 3 stereoisomers. And so there were a pair of enantiomers. We're going to use here one of the enantiomers, because you know the mesoform doesn't rotate light. Okay, it's optically inactive. But we're going to use one of the enantiomers of the non-mesoform, the one that rotates light to the right, so I'll put a plus. We're going to do a reaction between tartaric acid and this racemic mixture of Sec-butylamine. Now, if you take this, what's going to happen is this H, one of the H's of the carboxylic acid, is going to protonate the lone pair on the nitrogen. And so the NH2 will become an NH3+, and this CO2 will become a CO2-. Now you have to keep straight the difference between the plus minuses in brackets and a plus sign when I'm adding, meaning reacting, and when I put charges on. I'll put plus and minus in circles, which mean charge. Okay? Now, once you get the salt, the minus, and the positive of the NH3 plus and the minus, the CO2 minus, will form an ionic interaction. They'll form an ionic salt. And we can think about what we're actually going to get. So let's draw our salts. Now we're actually going to get two salts because we're going to have a plus minus. And so I'm going to draw them this way so you can see them a little better than the slide that's in your handout notes. And so we're going to draw it again. And this time I'm going to draw over here plus Sec-butylamine. And so here's plus Sec-butylamine. And now because of the carboxylic acid group protonating the NH2 lone pair, it's become an NH3 plus. And attracted to this plus charge is the CO2 minus. So I'm going to have an O2 minus group. And it still has its OHs off of here. CH3. And remember the chirality, just losing a proton is not going to change any of the chirality. And the optical rotation of this group was plus. So effectively, if you like, when these two interact, we get a new molecule, a new salt, where one end rotates it to the right and another end rotates it to the right. So if you like, this is, if it was structure, we could say it's RR. Now the other Sec-butylamine rotated light to the left. So when it protonates, one of the protonated versions will be the structure that rotates light to the left. That's charge. This guy has a minus. And of course, there was only one tartaric salt in there, tartaric acid molecule, and so when it becomes a salt, it's the same one. It's the plus O2. That has a minus. CCH OH CH OH CO2H. Now here's the question. We started originally with two enantiomers because the mirror reflection of plus rotation is minus rotation. Okay, so no problem. But now once it joins the salt, are they still mirror images? Well, ask yourself this. If I combine two salts that rotated light to the right, two anions that rotate light to the right to give a total rotation to the right, what's the exact mirror image of that? Well, the exact mirror image of plus plus in brackets is minus minus. Is this guy minus minus? He's not. He's not minus minus. So when he combines, he's going to have some rotation either to the right or left, but it's not the exact opposite. Remember, enantiomers rotate light in equal but opposite direction. Effectively, what we're saying is once we've added this identical enantiomer to Sec-butylamine, the two enantiomers are no longer mirror images. And when you are no longer mirror images, you now become stereoisomers that are not mirror images, that are non-superimposable. You become diastereomers. And whereas enantiomers had identical physical properties, diastereomers now have different physical properties. And it turns out that the sec-butylamine, that rotated light to the right, when combined with tartaric acid that rotates light to the right, produces a salt that is less soluble than the salt, which has the enantiomer that rotated light to the left. Okay, this is more soluble. So if I do the recrystallization, I can crystallize pure crystals of this diastereomer. So I can separate these guys. I can separate them by recrystallization. Okay. I can separate them by recrystallization. And once they're separated, I can restore my sec-butylamine. How? Well, once we've actually done the separation, I now have the one enantiomer in this separate container, or the one diastereomer all by itself, the one enantiomer of sec-butylamine. So now I've recrystallized, filtered off my crystals, I've collected the crystals, I can dissolve them up again. Now they're a pure enantiomer, or a pure diastereomer. All I have to do is remove the tartaric acid. How do you do that? Well, it's not that difficult. Let's think about what would happen if I hit this with sodium hydroxide, or a base like potassium hydroxide. So now I have this in its own container. I collected the crystals, I redissolve them, and I react them with something like potassium hydroxide. Potassium hydroxide is a source of OH minus, K plus OH minus. The OH minus is a powerful base. Oops, that should have been a CO2 minus, not a CO2H, sorry. Okay. Please note that should have been a CO2H on the other one. If I did have a CH3 there, I apologize. This should have been a CO2H. Okay, now, the base will pull a proton off both the NH3 and the CO2H. When it does that, you will get plus CH3, CH, CH2, CH3. Your pure enantiomer of sec-butylamine will be restored. The base, because it deprotonates this guy, will give you CO2, oops, CH, CH, CO2, the deprotonated version of tartaric acid. So if you use excess base, you get this. Now this can be recovered. Okay, you can separate them by crystallization. You can distill off the pure enantiomer of the sec-butylamine. This can be recollected and reprotonated by adding H+, and you can recollect your tartaric acid. Now you can get this pure enantiomer off by distillation, and you can isolate it in pure form. So you can either do extraction or distillation to purify the amine. This type of process shows you a real application where one pure enantiomer is used to help separate a racemic mixture of other enantiomers by converting them into diastereomers, which have different physical properties. In this case, the solubilities were changed, which allowed the separation. Now, one can raise a question which we'll have to address in the next Scribblecast lecture. How do you know, how can you check that you've actually gotten 100% purification? That you haven't. Okay, maybe this pair, this salt, was less soluble. But how do you know you didn't co-crystallize some of the other salt as an impurity? So, okay, maybe it's not a 50-50 mixture. Maybe it's 98% pure. But how do you know? How do you know whether you've gotten 100% purity or not? What can you do? Well, the answer to that question will be addressed in the next Scribblecast lecture. And thank you for listening. I hope it's been useful. My name is Dr. Brian Lloyd. This is my Scribblecast.